You know, it's pretty wild to think that some of the biggest challenges we face on this planet, like, say, storing carbon deep underground, are actually controlled by these tiny, invisible forces happening in microscopic spaces. Today, we're going to pull back the curtain on these powerful interactions. So let's dive in and uncover these unseen forces, starting with a mystery you probably see every single day.
We're going to kick things off with a super simple observation, something probably from your own kitchen, that, believe it or not, unlocks this entire world of complex physics.
Right, it's one of the first things we all learn in science class. But why? I mean, what is actually stopping them from just blending together? This isn't just a simple fact, it's a puzzle. And the answer lies in a force that's happening right there at the boundary, right at the interface between the two liquids.
And that right there brings us to our very first key concept. We are talking about the fundamental force that governs the boundary where two fluids that really don't like each other happen to meet. And it's called interfacial tension.
The best way to think about interfacial tension, or IFT for short, is like an invisible skin. Seriously, it's the reason water forms those perfect little beads and why oil clumps together in droplets. This skin is basically the result of molecules at the surface getting pulled inwards by all their neighbors, and that creates tension. It's this tension that is actively resisting any kind of mixing.
So, this force comes from a kind of molecular tug-of-war, and it dictates how well fluids mix, or don't, and it gives droplets their classic shape. Now, here's a really crucial bit. As things heat up, this tension gets weaker. The molecules get all energetic, that skin loosens up, and that can change absolutely everything. Okay, so we've got our two fluids, oil and water, and they're being held apart by IFT. But what happens when we introduce a third player into the mix, like a solid surface? Well, this is where it gets even more interesting, because now the liquids, they start to pick a side.
And this preference has a name. It's called wettability. It's really just a measure of which fluid the solid surface would rather be in contact with. Does the rock, for instance, prefer to be coated in water, or does it prefer oil? This simple choice, well, it has massive consequences.
And we don't just guess at this preference. Nope, we measure it very precisely using something called the contact angle. And this angle, it tells us everything we need to know about that rock's affinity for water, and it reveals two very, very different scenarios.
Check out the two extremes here. On the left, you've got a water-wet system. The rock loves water. The water spreads all the way out, and that creates a really small contact angle. We're talking less than 75 degrees, and it just clings to the surface. But on the right, it's the total opposite. The rock prefers oil, so the water beads up, making this big, wide angle, over 105 degrees, and it's the oil that's clinging to the walls.
So we've got interfacial tension separating fluids, and we've got wettability deciding which one sticks to a surface. So, what happens when we squeeze this whole system into a tiny, confined space, like the pore of a rock? Well, a powerful new force emerges.
This force is called capillary pressure, and it's the direct result of IFT and wettability teaming up inside a tight spot. It's the exact same force that can pull water up into a paper towel completely against gravity, or, as we're about to see, trap fluids deep, deep underground.
Now, the behavior of this pressure isn't random at all. It's perfectly described by this beautifully simple and, frankly, powerful piece of math called the Laplace equation. And if you look closely at it, you might just see some familiar characters in there.
This is what's so cool, because it just ties everything together. The force, PC, is a product of the fluid's skin strength, that's sigma, and the surface preference, theta. But look where r is, the radius of the pore. It's on the bottom. And that means the smaller the space, the stronger the resulting force. The size of the space, it matters a lot.
And look, this isn't just theory. Check this out. The Laplace equation tells us that as that radius r gets smaller, the capillary pressure gets way stronger. And this chart shows exactly that. In coarse sand with big pores, water rises 34 centimeters. Okay, but in fine sand with those teeny tiny pores, that same force is strong enough to pull water all the way up to 62 centimeters. Smaller space, stronger force. It's that simple.
So, we've been exploring these microscopic forces. Why should any of us care on a global scale? Well, because understanding them is absolutely critical to one of the most promising ideas we have for tackling climate change, carbon capture and storage. As some researchers pointed out in a 2024 paper, storing CO2 deep underground in these porous rock layers is a major strategy to cut down on emissions. But how in the world do you make sure it actually stays there?
Okay, so here's the problem. You inject CO2 deep underground into rock that's full of salt water. But that CO2 is like a bubble in a can of soda. It's buoyant, and it wants to rise right back up to the surface. So the entire challenge is just to overcome that upward push. And the solution, it lies in the very forces we've been talking about this whole time.
Now, there are a few ways you can trap CO2, like having a solid cap rock or dissolving it into the brine. But look at that last one, capillary trapping. This is our star player. The very same force that pulls water up into fine sand can be used to hold bubbles of CO2 in place, fighting against that buoyancy and stopping them from ever escaping. And here's where wettability becomes the absolute hero of the story. For this whole thing to work, the reservoir rock has to be water wet, because that means the salt water is going to cling to the pore walls, and that creates the perfect little cage to trap the CO2 bubble right in the middle, holding it tight.
So let's just zoom all the way out and recap this journey. We started with the invisible boundary between two fluids, and we ended up thousands of meters underground planning these global-scale engineering projects. We really built our understanding step by step, right? From the tension at a fluid interface to the preference of a solid surface, to the pressure generated in a tiny pore, all the way up to its application in a massive geological storage site. You can see how each concept built directly on the one before it.
And that, right there, is the big takeaway. The fate of these multi-billion-dollar projects, and frankly, a key part of our climate strategy, it doesn't depend on giant machinery. No, it's all determined by the subtle, microscopic physics of interfacial tension, wettability, and capillary pressure.
It really makes you think, doesn't it? It just goes to show that sometimes, to solve the biggest problems we face, we have to first understand the smallest, most fundamental forces that shape our world. What other giant challenges out there might just be waiting on a tiny discovery?